Night sits over the cosmos like a question that refuses to sleep. Before galaxies learned their spiral grammar, before the pale fire of the first stars, before time could stretch or space could breathe, there is imagined a silence so complete it has no place to rest. Out of that silence, existence appears, not gradually, not politely, but as a flare across a void that had no language for light. Instruments will later name its ashes the cosmic microwave background. Equations will cradle it inside curved spacetime. Philosophers will ask whether nothing can ever be more than a shadow cast by thought. Yet the unsettling core remains. Why is there anything at all? He stands, the physicist, before chalk dust and cold coffee, finding in Einstein's field lines of geometry that does not merely live in the universe but tells it how to be. She listens, the radio astronomer, to hiss that is not noise but memory. They walk, the observers, under a sky that seems indifferent and discover it is exquisitely tuned. A cosmological constant so small it reads as mercy. An early universe so smooth it feels premeditated. A surplus of matter so slight, 1 part in a billion, that the entire story of stars, stones, and thoughts is written in its margin. The mystery is not only how the universe began, but why it began, why the laws that hold it together are present at all, why the numbers fall just so, why emptiness conceals a restless sea of fields. If nothing is impossible, what is the cost of something? If existence is permitted, who or what signed the permission? The screen fades to black, then to the first light. The question remains, quietly immense. Why does the universe exist? Across blackboards and domes of glass, a quiet rebellion begins. The universe, long imagined as a tranquil forever, starts to move. In 1915, equations step onto the stage with the gravity of a new language. General relativity does not treat space as a container or time as a clock. It treats both as a living geometry. Mass and energy tell spacetime how to curve. Curvature tells matter how to fall. In that exchange, the cosmos is no longer a picture in a frame. It is the frame, bending under its own story. Yet the author of this language, Albert Einstein, leans toward stillness. The night sky appears stable, and a stable sky seems reasonable. To keep his solutions from drifting toward collapse or dispersal, he adds a term, lambda, the cosmological constant, a pressure within the equations themselves, tuned to hold the universe in place. It is an exquisite symmetry, but the balance is delicate, and the mathematics whispers of other options. If not held, the universe either shrinks or swells. The choice is not between motion and serenity. It is between kinds of fate. A young Russian mathematician, Alexander Friedman, listens to the equations rather than tradition. In the early 1920s, he solves Einstein's field equations for a universe that breathes, expanding, contracting, evolving. The solutions seem impertinent. They are also consistent. A few years later, a Belgian priest-physicist, Georges Lemaitre, follows similar paths through the geometry and adds a radical idea for the beginning, a primeval atom. Not a lump of matter, but a condensed state of spacetime and energy from which expansion unfurls. This is the first careful migration from always to once, from a cosmos without a past to a cosmos with a birth. The sky offers its verdict through red light. On a cold mountain in California, Edwin Hubble measures the distances to fuzzy spirals and finds them to be galaxies, island universes dispersed far beyond the Milky Way. He compares their distances to their spectral lines and finds a pattern. The further they are, the redder they appear, the faster they recede. In 1929, recession and distance join hands. Space itself stretches. Galaxies do not move through a static void so much as ride the widening of the void. Expansion becomes observational, not just theoretical. Friedman's and Lemaitre's dynamic cosmos steps out of thought and into evidence. If the universe expands, the tape run backward approaches density and heat. That inference becomes testable in the middle of the century. George Gamow, with Ralph Alpher and Robert Herman, calculates how a very young, very hot universe would assemble its first elements. In a brief furnace only minutes old, protons and neutrons fuse into helium, trace deuterium, and a breath of lithium. The heavier elements need stars. The earliest alchemy is modest and clean. By the late 1940s, this trio predicts that the young cosmos should also leave behind an afterglow, a bath of cooled light filling all space. Relic radiation redshifted from brilliant to faint, from blinding white to microwave hush. The sky again offers its verdict, this time by accident and elegance. In 1965, Arno Penzias and Robert Wilson turn a radio horn toward the quiet and hear a persistent noise that will not vanish. It clings to the instrument after every correction, every pigeon, every suspicion. At Princeton, Robert Dick, Jim Peebles, and colleagues have been preparing to search for precisely such a signal, a cosmic afterglow from a hot beginning. When the accounts meet, the interpretation locks into place. The noise is not noise, it is memory. The cosmic microwave background, near uniform across the entire sky, hums at a temperature just above absolute zero. The universe carries a photograph of itself at an age of roughly 380,000 years, when electrons married protons into neutral atoms and the fog cleared enough for light to travel. A picture so smooth threatens to be too perfect. If the early universe is almost uniform, what seeded the galaxies? If the photograph shows a nearly featureless surface, where are the primordial fingerprints? For a while, the answer sits below the threshold of instruments. Then in 1992, the COBE satellite resolves tiny temperature deviances, 1 part in 100,000, ripples that bloom into galaxies, clusters, and filaments under the pull of gravity. The smoothness has texture, the photograph has grain. These anisotropies are the seedlings of all later structure. Precision arrives not as a single event but as a long exposure. WMAP in the 2000s sharpens the map, tracing acoustic peaks, harmonics in the primordial plasma where pressure and gravity played out their early music. The heights and spacing of those peaks encode the proportions of the universe. How much ordinary matter, how much invisible cold matter, how flat the geometry. Planck refines the portrait further in the 2010s, revealing a cosmos astonishingly simple in summary, yet rich in detail. A flat universe to exquisite limits, about 5% baryons, roughly a quarter dark matter, and the rest an unseen component with negative pressure, acting like a cosmological constant. Out of temperature swirls and polarization strokes, a framework coalesces. Lambdictum, the cosmological constant plus cold dark matter, not as doctrine but as a scaffold where measurements converge. On the ground and in nearer space, other instruments measure the young sky's echo written in galaxies rather than light. Surveys like the Sloan Digital Sky survey thread spectra through millions of galaxies and quasars, reconstructing a cosmic web. Within that web lies a residual imprint from the infant universe, baryon acoustic oscillations, fossil sound waves now frozen as a preferred separation scale. That scale functions as a standard ruler, a meter stick etched into the distribution of galaxies. When checked against supernova distances and the CMB's angular ladder, the rulers agree to a stubborn degree. Independent lines cross at the same point on the map. The geometry of the universe, its size, its composition, these are no longer guesses but values quoted with uncertainties that shrink year by year. Yet the sky reserves a final surprise before the century turns. Type Ia supernovae, once calibrated candles for a decelerating expansion, betray a different story. Two teams, one led by Saul Perlmutter, another by Brian Schmidt and Adam Rees, compare distant supernova brightness to expectation and find them dimmer than a slowing universe would allow. The expansion is not merely ongoing, it is speeding up. In 1998, acceleration takes the lead, and the old cosmological constant returns not as a mathematical brace, but as a physical presence. Dark energy, an umbrella term for whatever drives space to accelerate its own growth. The narrative loops back to its earliest pages. Einstein's lambda, once a patch for stillness and later a confessed blunder, becomes the simplest fit to acceleration. But the simplicity hides a riddle. The observed value is small, astonishingly small, yet non-zero. Theory's naive estimates differ by wild orders of magnitude. The vacuum, which in quantum field theory seethes with fluctuations, acts in the grand average like a gentle push. Why so gentle? Why not overwhelming or absent? The constant that once rescued a static cosmos now dictates a dynamic future and deepens the question of origins. Each discovery in this chain transforms the cosmos from myth into history. General relativity grants a moving stage. Friedman and Lemaitre point to a beginning. Hubble supplies motion's proof. Nucleosynthesis speaks of a furnace only minutes old, while the microwave background carries the image of the first clear light. Anisotropy maps chart the seeds of all later architecture. Galaxy surveys lift a standard ruler from ancient sound. Supernovae turn the curve upward, and the universe accelerates into a fate not foreseen. In the process, the falsifiable replaces the speculative, the testable replaces the merely elegant. But the gain in clarity sharpens more than it resolves. The history now told with such confidence, hot beginning, growth of structure, late acceleration, depends delicately on initial conditions and universal constants. Why should space be so nearly flat? Why should the first light be so uniform, yet imprinted with just the right spectrum of small fluctuations? Why should matter have triumphed ever so slightly over antimatter by a ratio that permits stars and chemistry? Why should the vacuum carry a pressure that is not zero but almost, not crushing but insistent? The instruments answer how with precision. They point back to a beginning that obeyed a recipe of improbable simplicity. In laboratories and observatories, the questions turn toward the edges of explanation. If the seed ripples arose from quantum fluctuations stretched by an early inflationary phase, what field drove that expansion, and why was its potential tuned as it was? If dark energy is a cosmological constant, why that constant? If it is a field, why its present behavior? If the cosmological story reads cleanly from the light of the past, what wrote the initial sentence so legibly? The move from an eternal cosmos to a universe with a history is not the end of humility. It is its beginning. The discovery phase ends where the mystery deepens. A universe that began leaves a traceable record, equations that predict, telescopes that confirm, surveys that agree. It also leaves in the margins of those records numbers that feel chosen without chooser, conditions that feel prepared without preparer. Behind the expanding sky stand constants and initial orders that the data illuminate but do not explain. From eternal to historical, from static to expanding, from guess to measure, the journey is complete. The question has only grown more precise. Not only how the universe began, but why it carried, from the first moments, the quiet insistence to exist at all. The universe, newly granted a history, reveals an even stranger inheritance. Beginnings are not gentle in the mathematics that governs them. In the late 1960s, the singularity theorems of Stephen Hawking and Roger Penrose tightened the logic of general relativity to a point of startling consequence. Under broad conditions, gravity attractive, energy positive, causal structure intact, geodesics cannot be extended indefinitely into the past. Spacetime in these arguments is geodesically incomplete. The conclusion is not a cinematic point of infinite density, but something more austere. Classical description fails if one winds the cosmic film far enough back. An eternal, unbroken past gives way to a boundary the equations themselves cannot cross. The shock is not merely temporal, it is conceptual. A theory famous for continuous curves gestures toward the necessity of a new language at the beginning. A second disturbance arises not from geometry but from thermodynamics. Time's arrow is a daily companion. T cools, stars exhaust their fuel, galaxies assemble and age. But its source in a fundamental sense is a boundary condition. For entropy to rise, it must begin low. The early universe is astonishingly smooth, with density variations at the level of parts in 100,000. Its smoothness is often misread as disorder. In the presence of gravity, the opposite holds. Homogeneity stores potential for clumping, black holes, and the long heat death ahead. Smoothness at the start is low gravitational entropy. Roger Penrose formalizes the intuition in the Weyl curvature hypothesis. The initial universe appears to have vanishing Weyl curvature, a profound specialness in the arrangement of gravitational degrees of freedom. The arrow of time in this light is not legislated by dynamics alone. It is written into the very opening condition of the cosmos. Why the beginning should be so exquisitely ordered remains one of physics' most unsettling questions. The sky's most beautiful map carries the next fracture in intuition. The cosmic microwave background is nearly uniform across regions that, in standard Big Bang evolution without an early inflationary phase, could never have communicated before recombination. Opposite patches of the CMB would have been beyond causal contact, and yet they carry the same temperature to 5 significant figures. This is the horizon problem, a mystery of coordination written in ancient light. Alongside it stands the flatness problem. Spatial curvature, if not tuned to near zero early on, tends to grow with time. Yet today's universe appears flat within tight limits. To achieve such near flatness by fiat at early times would require an initial value balanced to absurd precision, numbers strung to improbable exactness before the first atoms ever formed. These are not contradictions in the laws, but contradictions in naivete. The cosmos looks too coordinated, too balanced, for a universe started off without some process to prepare it. Another imbalance, small, almost petty in its size, yet decisive, stares out from the periodic table. Matter dominates over antimatter by roughly 1 part in a billion. When the young, hot plasma cooled, almost every particle and its antiparticle annihilated. The whisper of an excess remained, leaving protons and neutrons to build stars and chemistry. Big Bang nucleosynthesis and the CMB both encode this asymmetry. Their independent inferences agree. And yet in the laboratory, the known sources of CP violation in the quark sector seem too feeble to generate the observed cosmic excess. Andrei Sakharov's conditions, baryon number violation, C and CP violation, and departure from equilibrium, outline the requirements for baryogenesis, but no tested mechanism within the standard model satisfies them at the needed scale. Hypotheses multiply. High-energy baryogenesis during grand unification, electroweak baryogenesis with new particles beyond the standard model, leptogenesis through heavy right-handed neutrinos, whose decays seed the baryon asymmetry through Sphalerin processes. The shock here is technical and existential. The very possibility of stars relies on a detail of microphysics that nature has not yet revealed. Looming over all these particular puzzles is a constant whose value seems to sit, with improbable poise, between triviality and catastrophe. The cosmological constant, or an equivalent dark energy component, drives the late-time acceleration of the universe. Observations of type Ia supernovae, the CMB, and large-scale structure converge on a present-day energy density in vacuum about 10⁻120 in Planck units, tiny beyond intuition, yet cosmically dominant today. Quantum field theory, naively summed to a plausible cutoff, predicts a vacuum energy larger by 60 to 120 orders of magnitude, depending on the accounting. Even careful renormalization does not erase the sense of a mismatch between what theory anticipates and what telescopes insist upon. If this energy were much larger and positive, galaxies would fail to form. If negative and modest, the cosmos would recollapse. The observed value lives in an unimaginably narrow band between sterility and collapse. The coincidence sharpens further. The densities of matter and dark energy, which redshift differently with expansion, happen to be of the same order now, in a brief cosmological era illuminated by observers and instruments. Why now? Why at all? Scale adds another fine line to the ledger. The amplitude of the primordial curvature perturbations, those initial ripples that inflationary models so naturally generate, registers at a dimensionless level of order 10⁻⁵. If it were much smaller, structure would struggle to form. Much larger, an early collapse would flood the universe with black holes and violent dynamics inhospitable to the slow work of chemistry. The spectral index lies close to, but not exactly at, the scale-invariant value. Even when mechanisms exist to produce such numbers, the question returns in another formulation. Why those parameters? Why that potential? Why that balance? The discomfort gathers a name in physics: naturalness. Hierarchies that seem unprotected by symmetries feel precarious. The mass of the Higgs boson, stabilized in the Standard Model only through delicate cancellations, provokes the hierarchy problem. The electroweak scale sits far below the Planck scale with no obvious guardian. Supersymmetry once promised a shield and has not yet appeared in data. Technicolor and other strong dynamics have faded. Extra dimensions and composite Higgs models remain possibilities under pressure. In cosmology, naturalness wraps itself around lambda and the inflatened potential. The equations allow these values, but do they explain them? The difference between permission and reason grows philosophically heavy. The singularity theorems, the low initial entropy, the horizon and flatness puzzles, the matter-antimatter imbalance, the small yet insistent cosmological constant, the just right amplitude of primordial fluctuations. Taken together, they read like a dossier of improbabilities that somehow add up to a consistent world. Physics absorbs shocks by building mechanisms. Inflation, for example, transforms the horizon and flatness problems into consequences of early exponential expansion. Regions once in causal contact are stretched beyond one another's horizons. Curvature is ironed away to near zero. Quantum fluctuations are magnified into classical seeds. But mechanisms, when they work, do not silence the prior question. Why was there an inflaton? Why that potential? Why a vacuum energy that does not annihilate structure yet quickens expansion? The quantum vacuum adds a quiet, disconcerting counterpoint. Even empty space, stripped of particles, retains fluctuations. Fields never quite sleep. The Casimir effect and Lamb shift are laboratory shadows of this unrest. In cosmology, the vacuum wears two faces: local phenomena that match quantum theory's whir, and a global energy density that pretends to be almost nothing. Between these faces lies the cosmological constant problem, the most extreme disparity between theory and observation in modern physics. It is not mere embarrassment. It is a sign that the classical and quantum pictures, so successful in their domains, may be talking past one another at the deepest level. Some responses reach beyond mechanism to selection. In a landscape of possible low-energy laws, perhaps emerging from a high-energy theory with many vacuum solutions, constants might vary from region to region. Eternal inflation, by its very design, would seed a multiverse of pocket universes with different parameters. In such a setting, observers would naturally find themselves in domains where conditions permit complexity. This is the weak anthropic principle, a statement about selection bias, not design. It is logically consistent and in a limited way predictive. Yet it imposes a new difficulty. Probability in an infinite ensemble is treacherous. Measures disagree, typicality becomes ill-posed. The solution risks replacing one shock, a small lambda, with another, an ocean of worlds that cannot be seen, weighed, or ruled out except by indirect logic. Other responses keep the question local but widen its scope. Perhaps the initial low entropy is not a brute fact, but a consequence of deeper principle. Gravity emergent from quantum information, spacetime itself a condensate of entanglement. Perhaps the beginnings theorems are clues to the limits of continuity, pointing toward a bounce or a no-boundary condition where the word before loses traction. These ideas are rigorous where they are mathematical and speculative where they must be. They remain, at present, roads still under survey, their signposts promising but not yet anchored in decisive observation. What remains, after the shocks are counted, is not despair but a recalibration of wonder. The universe does not merely exist. It exists under constraints that make narration possible. A small surplus of matter persists after annihilation. Gravitational degrees of freedom begin in a special state. Space expands in a way that turns quantum whispers into galaxies. Vacuum energy declines to dominate only when structure has already formed. Geometry stays nearly flat across horizons wider than imagination. None of these statements violates known physics. Each of them strains against ordinary expectation. In this tension, the scientific and the philosophical overlap without dissolving into one another. Laws explain how, and observations record what. The question why these laws, these numbers, this beginning remains metaphysical in the literal sense, beyond the current physics, yet tied by 1,000 threads to what telescopes, accelerators, and satellites have already taught. The discovery of a universe with a history was the first upheaval. The recognition that this history is perched on a lattice of delicacies is the second. Shock gives way to a steadier emotion, patience. The cosmos has confessed enough to reshape thought. It has withheld enough to keep the inquiry honest. The universe begins to confess in numbers. What once arrived as a chorus of firsts, first light, first atoms, first stars, becomes a ledger, a careful balance of amplitudes and angles, spectra and counts. The maps of the cosmic microwave background are no longer only portraits. They are instruments with dials. Their temperature ripples, 1 part in 100,000, are decomposed into harmonics as if the infant cosmos were a resonant drum. Peaks rise at precise multipoles, the acoustic signatures of pressure waves in a plasma of photons and baryons. Their heights and spacing speak a compact language, ordinary matter to radiation, dark matter to baryons, curvature to flatness. In that grammar, a nearly flat geometry emerges within tight limits, and the fraction of matter that is luminous recedes to a minority share. Gravity, at large, answers to mass that does not shine. Polarization adds a keener edge to the picture. E-mode patterns confirm a universe that recombined, then reionized under the first stars and galaxies. Lensing of the CMB, minute distortion sculpted by intervening structure, etches a history of growth onto the last scattering surface. Even in the oldest light, a record of the later universe is stored, faint but legible. The search for primordial B-modes continues like a patient listening for a heartbeat beneath noise, a hunt for the gravitational waves of the first instance that would turn inflation from a persuasive mechanism into a measured fact. Upper bounds tight, and the silence is anatomized with more care each year. Beyond microwave light, galaxies arrange themselves into a web whose threads remember an earlier music. The preferred separation left by baryon acoustic oscillations becomes a standard ruler inscribed in space. Redshift surveys stitch the sky into 3 dimensions. Spectrographs drink in millions of lines and return distances. The ruler, read at different epochs, tracks the expansion history. It agrees with the CMB at one edge of time and with supernovae at another. Where lines cross, confidence deepens. Where they miss by a narrow margin, a new puzzle is born. One such margin acquires a name, the Hubble tension. Early universe inferences, anchored in the CMB's acoustic scale and evolved forward under lambdictum, point toward a value of the present expansion rate in the upper 60s of kilometers per second per megaparsec. Late universe ladders, calibrated from Cepheids to Type Ia supernovae and beyond, favor values in the low to mid-70s. The split is not catastrophic, it is persistent. Independent anchors are added. The tip of the red giant branch, surface brightness fluctuations, time delays in lensed quasars. Each method carries its own systematic cautions. Each adds weight to one arm of the scale. The divergence may be an artifact of calibration, a subtle bias hiding in the scaffolding of astronomical distance. Or it may be a whisper of new physics that retunes the early cosmos, the light relic content, a phase of early dark energy, a deviation in recombination physics. For now, it remains a disciplined disagreement that sharpens both technique and theory. At higher redshifts, new eyes see farther back and find the dawn more crowded than expected. The first luminous structures appear bright and mature in the very young universe. Star formation builds vigorously where models had anticipated shyness. Supermassive black holes already weigh hundreds of millions of suns when the cosmic clock has scarcely begun to tick. None of this violates the known laws. None of it fits comfortably within their simplest extrapolations. The epoch of reionization, extracted from CMB polarization and the Lyman alpha forest in quasar spectra, spans a broad dawn. Observations press against the timeline's edges, and the first chapters of galaxy formation are revised with each spectrum secured under the pressure of noise and distance. The canvas holds, the brushwork shifts. Closer to home in energy but no less fundamental, the laboratory adds its own precise interrogations. The surplus of matter over antimatter, one extra particle per billion pairs, remains a cornerstone measured in two cosmic scripts: the relative abundances from Big Bang nucleosynthesis and the baryon density inferred from the CMB. Under both, the asymmetry is real and small. The standard model of particle physics, so successful in other domains, cannot generate it at the needed scale with its known sources of CP violation. The conditions laid down by Sakharov, baryon number violation, charge conjugation and parity violation, and departure from equilibrium, are a program, not a solution. Possible roots multiply. Electroweak baryogenesis asks the Higgs field to drive a strong first-order phase transition in the early universe, with new particles or interactions supplying enough CP violation. Current collider limits press hard on that landscape, but have not erased it. Leptogenesis imagines heavy right-handed neutrinos out of equilibrium, decaying to seed a lepton asymmetry. Non-perturbative electroweak processes then convert a portion into baryon number. The seesaw mechanism that renders active neutrinos light would be apparent to that tail. Experiments bear down on each link. Long baseline neutrino beams pursue leptonic CP violation. Reactor and atmospheric experiments map mixing angles with increasing precision. Tritium beta decay spectra press the effective electron-neutrino mass into the sub-eV regime. Each new constraint redraws where the asymmetry could have been born. Other rare processes are asked to speak. The search for neutrinoless double beta decay listens for a violation of lepton number that would reveal neutrinos as their own antiparticles, a Majorana identity that would lend credence to leptogenesis and reframe the symmetries of the standard model. No confirmed signal has yet crossed the threshold. The half-life limits recede into magnitudes that humble metaphor. Proton decay, a hallmark of many grand unified theories, remains unobserved to lifetimes beyond 1034 years in favored channels, banishing the simplest unifications and forcing their elaboration. Null results are not quiet, they prune. Even the apparent stability of the vacuum is turned into a plot point. With the measured Higgs and top quark masses, the renormalization group flow of the Higgs self-coupling hovers near a boundary between stability and metastability. Within uncertainties, the electroweak vacuum may be long-lived but not absolute, the ground state not the ground, only a shelf in a deeper landscape. If true, the lifetime dwarfs the age of the cosmos by untellable factors. Existence is not endangered by this arithmetic. Yet the proximity to criticality tempts interpretation. A universe poised near thresholds of flatness, of vacuum energy, of stability, seems to recur as a theme. Whether selection, dynamics, or coincidence carves that theme is the unclosed question. Where geometry touches the quantum, the vacuum speaks with two tongues. Locally, zero-point fluctuations are measured phenomena. The Lamb shift in atomic spectra, the Casimir force between uncharged plates, stochastic jitter written into the granularity of measurement. Cosmologically, vacuum energy behaves as if it were almost nothing yet not quite zero, driving an acceleration that shapes the fate of all large-scale structures. The two voices use the same word, vacuum, but do not obviously belong to the same sentence. Renormalization removes infinities with impeccable consistency in particle physics. The residual global energy that gravity hears ought to be the sum that remains after the same procedure. Simple accounting fails by exponents, and sophistication does not bridge the gap. The cosmological constant problem is not an embarrassment pasted over. It is a map pinned to the wall with no route marked through. Back in the sky, the growth of structure becomes a chronometer and a stress test. Weak gravitational lensing, subtle shears in the shapes of distant galaxies, measures the clumpiness of matter through a parameter that blends sigma 8, the amplitude of fluctuations, with the matter fraction. Some surveys have reported values in gentle tension with the CMB-based expectations, a whisper rather than a shout, but persistent enough to be interesting. If growth is slower than lambdictum predicts, gravity may be modified on large scales, or dark energy may be more than a constant. If the tension dissolves under better control of systematics, a cautionary tale is won instead. Either outcome is knowledge. The young cosmos is also asked to reveal itself through its 21-centimeter line, the neutral hydrogen transition that could, when measured across redshift, paint a tomographic film of the cosmic dawn and reionization. Instruments chase a global signal beneath terrestrial interference and foregrounds brighter by orders of magnitude. Arrays seek fluctuations that trace heating and ionization. The technique is ferociously difficult and promises, if met, to turn broad timelines into detailed ones, to resolve whether early X-ray sources warmed the intergalactic medium in time with stars and black holes, to test models that otherwise only sketch. Across all these domains, the CMB and its polarization, galaxy redshift maps and lensing, supernovae and quasars, neutrino beams and underground crystals, the pattern of investigation is the same. Independent measures that triangulate the same parameters, parallel approaches that can fail independently, and a surveillance of the universe at multiple epochs that demands internal consistency across time. The scaffolding holds because it is redundantly built. Where strain appears, it is because redundancy does not allow the strain to hide. What do the patterns say when they are read together? They point, consistently, toward a universe governed by general relativity on large scales, seeded with nearly Gaussian primordial fluctuations of small amplitude, composed of ordinary matter plus a colder, non-baryonic component that anchors structure, and a late-time acceleration compatible with a cosmological constant. They point insistently toward a beginning that was hot and dense and extraordinarily simple in its statistics, with deviations from perfect scale invariance that are slight yet revealing. They point, persistently, toward a microphysical story in which the standard model is a chapter and not the book. And yet the deeper layers of mystery sharpen in the very act of measurement. The Hubble tension keeps its poise, the smallness of lambda keeps its sovereignty, the origin of the baryon asymmetry keeps its counsel, the inflationary era remains an inference awaiting its smoking gun. The vacuum holds its two tongues together without teaching them a common grammar. This is not failure. It is a discipline learned from the sky. That precision is not the end of wonder but its refinement. The cosmos has yielded data of a kind and quality no past century could have imagined. It has, with the same instruments, taught the questions how to ask themselves more clearly. In the wake of deeper investigation, the original mystery grows more articulate. The universe does not merely exist. It exists as a network of measured relations, a pattern whose details seem improbably fitted to long stories, stars, planets, chemistry, mind. The facts do not force a meaning, they force attention. Above the cold hum of the microwave background and the faint sheer of distant galaxies, beneath the lead walls of underground detectors and the thrum of accelerators, a quieter inquiry persists. It asks whether explanation will, at some depth, close into a circle, laws explaining laws, or whether there will remain a final contingency, an initial condition that is not derived but given. The instruments continue to ask the universe for a number. The universe continues to answer, And somewhere between the answer and the need for one lies the question that gave birth to the measurements. Why does anything exist at all? The universe advances like a tightrope walker, balanced on numbers that do not announce their reasons. A small pressure in empty space urges expansion onward. A whisper of primordial roughness seeds all later architecture. A sliver of matter survives annihilation and composes worlds. Change any of them by a breath and the story tips. The grammar of existence remains legible, but its diction feels improbable, as if the cosmos speaks in fine print where a bolder font might have been easier. The question hardens, not merely how the universe began, but why it is tuned to continue. Consider the constant that is not a constant of matter at all, but of the vacuum. In equations, it is lambda. In observation, it is the cause of a late-time hastening, a cosmic push that dilutes structure while leaving it intact. Its measured value is unimaginably small in natural units, yet cosmically sovereign today. The old problem asks why lambda is so close to zero. The newer problem asks why it is not exactly zero, and why it comes to prominence now, when stars and observers already exist. Theory's naive sums over quantum fluctuations overshoot by staggering orders of magnitude. The sky, with calm indifference, insists on near zero, not zero. The coincidence lingers like a riddle, a universe neither crushed by vacuum nor starved of it, but poised between. Precision, the ally of certainty, becomes a source of unease. The present expansion rate, h0, refuses to converge when asked from opposite ends of time. Early universe inference, read from the cosmic microwave background and extended through lambdictum, favors a value near 6768 km/s/MPC. Distance ladders built from Cepheids and type Ia supernovae prefer /73. New measurements with the James Webb Space Telescope have pressed on the obvious culprit, crowding and calibration of Cepheid light, and found that explanation wanting. The discrepancy does not dissolve when the photometry is remeasured with finer eyes. Meanwhile, baryon acoustic oscillations mapped by Dacey trace the expansion in a different key and lean toward the early value. The friction is not a crisis. It is a disciplined disagreement that has survived every easy fix. If calibration subtleties do not resolve it, something in the early physics may need to sing a different note. The growth of structure adds its own, softer counterpoint. Weak-lensing surveys that measure the clumpiness of matter have at times preferred a universe slightly less bunched than the microwave sky would suggest. Some of that tension has eased as techniques have matured and new tracers, like X-ray counts of galaxy clusters with EROSITA, have joined the chorus, but the episode remains instructive. Even small mismatches can become lenses that focus attention on hidden systematics or unmodeled physics. In these margins, gravity itself becomes a suspect, and dark energy is asked whether it truly is a constant or only a very patient field. Then the deep field brightens in an unexpected way. Beyond redshift 10, where theory anticipated hesitations and dimness, the new telescope finds luminous galaxies appearing earlier and more frequently than models had prepared for. Spectra confirm some objects beyond Z approximately 14, light from when the universe was scarcely 300 million years old, brimming with young stars and ultraviolet continuum steep enough to surprise. The simplest simulations tighten their laces. Are stellar populations more efficient in primordial conditions? Do active galactic nuclei masquerade as starlight, inflating masses and brightness? Or does the early cosmic inventory include a transient dose of new energy that briefly accelerates growth? The data do not pronounce a verdict. They intensify the questions. The surprise is not fatal to lambdictum, but it is a stern teacher, reminding that cosmology leans on astrophysics to translate light into truth. Numbers nearer home and energy threaten a different vertigo. With the measured masses of the Higgs boson and top quark, the Standard Model's equations suggest that the electroweak vacuum may be metastable, safe for timescales that dwarf any human concern, yet not the absolute ground state. The Higgs potential, run to high energies, wavers near the edge between stability and a deeper well. Some take the near criticality as coincidence. Others hear a hint that selection or hidden dynamics prefer thresholds. The fact remains sober. The vacuum in which galaxies drift and minds arise might be perched, mathematically, on a ledge that is high, wide, and unimaginably long, but a ledge nonetheless. If the late universe continues to accelerate under a positive lambda, it approaches a de Sitter, like future with a horizon and a finite temperature. In such a setting, thought experiments become uneasy companions. Over absurd expanses of time, random thermal fluctuations could, in principle, assemble momentary observers, Boltzmann brains, more readily than entire, thermodynamically respectable histories like the one recorded in fossils and microwave background maps. If such freak observers were typical, ordinary memory would be suspect, and science would undercut itself. The paradox is not a forecast. It is a constraint. Viable cosmologies must arrange their dynamics, measures, or decay channels so that coherent histories dominate over chance hallucinations. The universe's long future must be structured such that meaning continues to be typical. Escalation also arrives as a question about counting. Inflation, the early burst that can iron away curvature and link distant regions into causal conversation, seems in many models to be eternal, to spill out pocket universes without end, each a bubble with its own local low-energy laws. In such a multiverse, prediction demands a measure, a rule to compare infinities. Different measures disagree, sometimes violently. Probabilities slip through definitions. Typicality refuses to settle. If the landscape of possible vacua is vast, the anthropic argument may select domains where galaxies form and chemistry persists, offering a logic for small lambda, but only once a coherent measure exists to weigh possibilities. Until then, explanation risks becoming a mirror that reflects assumptions. Even the successes sharpen the ache. Planck's map of the oldest light, the ruler etched by baryon acoustic oscillations, the supernova arcs that trace the late-time curve, all converge on a model that is spare and predictive. That very success exposes how delicately the world depends on boundary conditions that physics explains only in part. Inflation elegantly addresses horizon and flatness. It does not specify why its field existed or why its potential took a form that yields just the right spectrum of primordial ripples. Dark energy fits the data with a single number. It does not say why that number sits where it does. The arrow of time aligns with low initial gravitational entropy. The reason for that lowness remains outside current dynamics. The closer the fit, the clearer the silhouette of what is missing. Elsewhere, new signals widen the stage without yet rewriting the script. A background of nanohertz gravitational waves now hums across pulsar timing arrays, almost surely the collective murmur of supermassive black hole binaries growing together as galaxies merge. The detection vindicates expectation, but it also complicates simplicity. Black holes assemble faster than once thought, and their chorus may one day separate into individual voices, adding clocks to the cosmic ledger. Each confirmation spawns a fresh variable. Each new variable tightens the net in which anomalies are caught. Beneath all this lies the oldest philosophical current in the river of calculation. Existence appears contingent not just on laws but on values the laws carry: masses, couplings, densities, initial smoothness. Perhaps deeper symmetries fix them. Perhaps dynamics selects them. Perhaps a vast ensemble permits all, and observers arise where they can. No conclusion is forced by the data, yet the data insists on the precision of the question. If the cosmos is a cathedral of numbers, it is one in which the stained glass is not arbitrary. The light that passes through is colored by constants that make sense of atoms and time. The mystery deepens not by dissolving into obscurity, but by growing more sharply contoured. The cosmological constant is measurable yet unexplained, the expansion rate consistent in parts yet discordant in some. The first galaxies earlier and brighter than comfortable models liked. The vacuum perhaps perched near a boundary. the far future logically constrained by the requirement that reason remain typical. Each thread tightens the weave of a tapestry that has already carried observers far enough to ask why there is any tapestry at all. The escalations do not promise catastrophe. They promise proximity to whatever principle, mechanism, or selection will finally explain why the universe exists in this particular key and not another. Explanations assemble like constellations, points of theory lit by observation, lines drawn between them by need. Each proposal is a lens, sometimes clarifying, sometimes distorting, held up to a single, stubborn question. Why does a universe exist with laws and numbers that allow it to last, to cool, to think? The first lens is inflation. In its simplest telling, a scalar field hangs on a plateau of potential energy, and space, urged by that vacuum-like pressure, expands almost exponentially. Regions once intimate are torn beyond each other's horizons, ironing curvature flat and stretching any primordial wrinkles into near-scale invariant ripples. Quantum fluctuations, ubiquitous and restless, are inflated into classical seeds, curvature perturbations whose amplitudes and statistics become the blueprint for galaxies. The music left in the cosmic microwave background, acoustic peaks and a slightly red spectral tilt, mirrors the generic predictions of this story. Where inflation is a mechanism, however, it also offers a dilemma. It solves horizon and flatness with ease, but leaves the questions of identity and motive. What field did the inflating? Why that potential? Why the graceful exit? And why does the inferred energy scale sit where it does? In many models, inflation tends to be eternal to the future, spawning pocket universes without end. The mechanism that prepares the observed cosmos thereby births an ensemble, and explanation becomes entangled with selection. Selection enters under the sign of the anthropic argument, a logic both austere and controversial. If a fundamental theory admits a landscape of low-energy vacua, each with different effective constants, then only in some domains do galaxies and long-lived stars arise. In that setting, observers will inevitably find themselves in the congenial corners. A small but non-zero cosmological constant, catastrophic if much larger and fatal if significantly negative, acquires a statistical rationale rather than a dynamical cause. Ideas from high-energy theory give this possibility scaffolding. In string-theoretic constructions, compactifications and fluxes proliferate a vast menu of vacua. The number often quoted is hyperbolic, but the principle is clear. The laws felt at low energies may be local addresses in a much larger postal system. To render this explanatory rather than rhetorical, probabilities must be assigned across infinite possibilities, the measure problem of eternal inflation, and predictions must be coarse but testable. Correlations among constants, distributions of values, constraints on what can vary together. Without a measure and a map, the multiverse risks becoming an unlit gallery. Other routes keep the cosmos single but soften its edges. Quantum cosmology asks whether a universe can be born from a prior state, not of space and time, but of amplitude and boundary. In the no-boundary proposal, the wave function of the universe favors histories that are locally classical yet rounded at the beginning, a geometry that transitions from Euclidean to Lorentzian without a sharp edge. In a sibling proposal, the universe tunnels from nothing, not an empty room, but the absence of classical spacetime, into expansion. These pictures offer philosophical relief from a singularity and technical paths to compute relative probabilities of early conditions. They do not, by themselves, fix the values of constants. Rather, they frame the origin as a quantum event whose measure one might someday compute with the same confidence used to normalize decay rates in particle physics. The idea is not empirically closed. If such proposals generically prefer inflationary patches with particular attributes, the downstream signatures, scalar tilt, non-Gaussianities, gravitational wave backgrounds, become the data's veto or assent. Where singularities challenge classical description, Quantum gravity proposes alternatives that replace a beginning with a transition. Loop quantum cosmology quantizes geometry itself, so that at Planckian density, repulsive quantum geometric effects appear, and a contracting cosmos may bounce into expansion. The ekpyrotic and cyclic scenarios, inspired by higher dimensional brain dynamics, imagine a slow, smoothing contraction that suppresses curvature and inhomogeneity before a bounce ignites the hot Big Bang conditions. Conformal cyclic cosmology suggests that the remote, exponentially expanded future of one eon can be conformally rescaled to seed the next, erasing scales but not structure. Each of these proposals turns the word before into physics rather than paradox. Each faces exacting tests, matching the observed spectrum and statistics of perturbations, avoiding relics that observations would have noticed, and offering, ideally, a distinctive fingerprint, an angular pattern, a spectral kink, a non-Gaussian motif that separates one creation myth written in mathematics from another. Explanations also descend into the microphysical, seeking origins for the small asymmetries that made complexity inevitable. The survival of matter over antimatter requires processes that violate CP symmetry and depart from equilibrium while allowing baryon number to change. Electroweak baryogenesis imagines the Higgs field driving a strong first-order phase transition, with new particles adding the needed CP violation. Current constraints weigh heavily on such models, but have not banished them. Leptogenesis places heavy right-handed neutrinos in the early inventory. Their out-of-equilibrium decays generate a lepton asymmetry that electroweak sphalerons partially convert into baryon number. The seesaw mechanism, rendering observed neutrinos light, serves as a structural backbone for this tale. Neutrinoless double beta decay, if ever observed, would speak in the vocabulary of Majorana masses and lepton number violation, leaning the narrative toward leptogenesis with experimental authority. Other fields enter as quiet engineers of parameters. The QCD axion, born to solve the strong CP problem, doubles as a dark matter candidate whose abundance can be set by initial misalignment, naturally small couplings, and feeble interactions. If axions or axion-like fields form a landscape, cosmology inherits a family of light fields whose vacuum expectation values scan effective constants. Relaction models push further, proposing dynamics where a rolling field scans the Higgs mass and stalls when backreaction turns on, placing the electroweak scale at a small value without elaborate symmetry. These ideas live at the boundaries between cosmology and particle physics. Their validation belongs as much to tabletop haloscopes and microwave cavities as to satellites mapping ancient light. A different bridge between small and large emerges from the holographic principle. Black hole thermodynamics, given firm footing by Hawking radiation and the Einstein-Hawking entropy, hints that the information content of a region tracks its boundary, not its volume. In anti-de Sitter space, a correspondence makes that hint precise. A quantum field theory without gravity, living on the boundary, encodes a gravitational theory in the bulk. From this vantage, spacetime and gravity appear as emergent phenomena, their geometry a macroscopic expression of entanglement patterns in a deeper quantum state. Tensor networks, Ryu, Takayanagi surfaces, and related constructions turn the metaphor into equations that compute areas and entropies, differences and flows. The temptation is philosophical and specific. If gravity and space emerge from entanglement, perhaps initial conditions are statements about quantum information, about how entanglement was arranged at the start. The move is bold and incomplete. Current holographic dualities are best understood in negatively curved spaces, not in the de Sitter, like geometry suggested by cosmic acceleration. Still, the principle reframes explanation. Laws may be effective, geometry derivative, constants reflections of an underlying code. Even within inflation, an internal diversity of models serves as a caution. Plateau-like potentials, monomials, hybrids, multi-field landscapes with turns and features. All can fit the broad swath of current data while differing in their predictions for the tensor-to-scalar ratio, the running of spectral tilt, and degrees of non-Gaussianity. The simplest single-field, slow-roll models predict nearly Gaussian, adiabatic perturbations with a small tensor background. Constraints have pressed the tensor amplitude downward, trimming the field. Multi-field scenarios can generate isocurvature modes and higher non-Gaussian signals, both stringently limited by observations. Features in the inflattened potential could inscribe oscillations in the power spectrum. Searches pursue such fingerprints. If a primordial gravitational wave background is found with the right spectrum, the measurement will not only bless inflation's core logic, but also weigh the scale of the physics involved, peering into energies no collider will reach. Dark energy, though phenomenologically captured by a constant, invites alternatives that turn coincidence into dynamics. Quintessence replaces lambda with a slowly rolling scalar field, whose energy density dilutes more gently than matter. K-essence and other kinetic constructions vary the script further. Chameleon and symmetron fields hide their influence in high-density environments while acting cosmologically, evading laboratory bounds yet moving the expansion. Modified gravity rewrites the field equations at large scales. F-R theories, brain-world models, massive gravitons, striving to mimic acceleration without dark energy. Each idea walks a narrow path between background expansion, growth of structure, gravitational lensing, and solar system precision tests. Each can be checked by how structure grows, how light bends, how clocks tick in different potentials. The story must pass in both the heavens and the laboratory. The arrow of time, perhaps the most intimate mystery, asks for ancestry as ambitious as any mechanism for expansion. If low initial gravitational entropy underwrites the directionality of experience, why was it low? Inflation smooths, but does not by itself, explain the specialness. Many inflating patches would begin in high entropy states that do not resemble the observed universe. One response sees the low entropy boundary as brute fact or as a consequence of selection in a larger ensemble. Another sees it as emergent. Gravity and spacetime are coarse-grained descriptions of entanglement dynamics, and the initial condition is a statement about minimal entanglement across emergent partitions. In such a view, the past hypothesis becomes a boundary condition in quantum information space rather than in fields and metrics. This rephrasing promises no easy test tomorrow. It aims to place thermodynamic asymmetry and cosmological structure in one grammar. Threaded through these proposals is a shared lesson. Explanation in cosmology often migrates the question rather than annihilates it. Inflation replaces a tuned beginning with a dynamical smoothing, but then asks why the inflatten. Anthropic logic can account for small lambda if a vast ensemble exists, but then asks how to weigh infinities, and whether such an ensemble is physics or philosophy. Quantum creation replaces a singular instant with a calculable amplitude, then asks how a wave function selects a realized history. Holography recasts spacetime as emergent, then asks what microscopic theory underwrites the emergence in a de Sitter dominated universe. Each success refines the silhouette of what remains unknown. Each speculation suggests a measurement that could move it from perhaps to persuaded. The question that governs the narrative, why does the universe exist, may never collapse to a single number the way a particle mass does. It may resolve into a set of linked answers, a mechanism for smoothness and seeds, a microphysical account of asymmetries, a principled explanation for small vacuum energy, a unification in which constants are outputs rather than inputs, a story of origins written in the language of quantum states rather than classical beginnings. Or it may end at a final rock, a fundamental principle that declares, without deeper cause, that something is favored over nothing, law over chaos, math over silence. Between that rock and the present evidence stretches a road thick with instruments and equations. Each theory here is a wager on what kind of answer the cosmos allows: dynamical, statistical, quantum, informational. The wagers are not equal and need not be mutually exclusive. A universe may be born by tunneling into a no-boundary history that inflates on a plateau chosen from a landscape whose statistics favor small lambda and whose microstructure renders gravity emergent from entanglement. If such a composite story ever hardens under data, the old philosophical question will not vanish. It will, at last, be speaking physics fluently. Across mountaintops, deserts, and the Lagrange points of cold space, instruments turn toward first causes. Their mirrors and cryostats, their timing arrays and buried halls, form a dispersed cathedral whose nave is the sky. Each device is an argument in hardware, that the universe, if asked carefully, will return not myth but measurement. In the high, dry air of the Atacama, the Simons Observatory begins to sweep the millimeter sky with tens of thousands of superconducting eyes. Its aim is austere and ambitious. Trace the primordial whisper in polarization, weigh the growth of structure through lensing, and tighten the grammar of the first seconds. The observatory's design is a wager that more detectors, colder stages, and broader frequency coverage can turn rumor into restraint. Even as plans for an even larger U.S. effort, CMB-S4, have been pared back, the community's strategy remains. Upgrade what exists, listen longer, and let the sky, not the schedule, decide how softly the early universe spoke. Above the atmosphere, a complementary sentinel prepares. Lightbird, a JAXA-led mission, conceived to map B-mode polarization across the entire sky from the stillness of L2. Together, ground and space are arranged like two halves of an ear, tuned for a heartbeat at the edge of time. If inflation left a gravitational aftertaste, it would appear as a curl in the polarization of the oldest light. The present verdict is restraint rather than revelation. Combining bicep Keck's deep patches with Planck's all-sky maps yields an upper limit on the tensor-to-scalar ratio at a few percent level. The silence is not empty. It narrows the space of viable and flattened potentials and keeps the field honest while experiments sharpen their nulls into knowledge. Far from Chile, a European eye unfurls in space. Euclid's first public data, deep previews laced with lensing arcs and hundreds of thousands of galaxies, announce a survey built to turn the geometry of the universe into a ledger. Weak lensing and baryon acoustic oscillations, measured over a third of the sky, will test whether cosmic acceleration is a constant pressure or a patient field. The opening release is a promise letter, small in area, rich in detail, and marching toward a grand atlas. On the ground, spectrographs operate like cosmology seismographs. Dacey's first-year measurements of the acoustic ruler, carved at recombination and read at later times, now trace expansion from the nearby universe to redshifts beyond 4. The results, taken alone, sit comfortably within flat lambdictum. Braided with other data, they lean and test, fixing H0 under minimal assumptions, probing W, and placing stern limits on the sum of neutrino masses. It is a style of progress characteristic of the field, confidence by convergence, tension by triangulation. The survey age is not only about depth, it is about cadence. On Cerro Pachon, the Vera C. Rubin Observatory has opened its eye, unveiling first images from the Wide-Field Simony Survey Telescope and preparing for a 10-year film of the southern sky. Supernovae will mark cosmic time. Weak lensing will map invisible scaffolding. Small deviations in how structure grows will become verdicts on gravity itself. A machine that watches everything frequently is a machine designed to be surprised. Next in the relay will be Roman, NASA's wide-field surveyor, scheduled to fly in the latter half of this decade. Its high-latitude surveys will tie together supernovae, lensing, and clustering in one language, turning percent-level uncertainties into fractions and the late-time history of expansion into a measured curve rather than a hand-drawn arc. Roman's role is not to add a new question. It is to ask the existing one, what drives acceleration, so carefully that fewer answers survive. Meanwhile, a smaller sentinel has already left Earth. Spherex, launched in 2025, will use spectroscopy at low resolution, but all sky to map the cosmic glow in 102 colors. Its strength lies in statistics, correlations across billions of voxels that can reveal imprints of inflation, trace the rise of the first galaxies, and inventory ices in our own spiral arm, the chemistry that later writes in carbon and water what physics began. At meter and kilometer wavelengths, a different chronicle is forming. The neutral hydrogen line at 21 centimeters promises a tomographic film of cosmic dawn and reionization, when the first lights rewrote the intergalactic medium. For now, the news is restrained. Experiments such as HERA and LOFAR report increasingly deep upper limits on the power spectrum, and the Square Kilometer Array, now testing its first SCALO stations and producing early images, moves from blueprint to landscape. When that movie arrives, thermal history will cease to be a diagram and become a measurable biography. Gravitational waves add a bass line beneath the map. Pulsar timing arrays, galactic-scale detectors built from millisecond clocks, have now found the correlated hum expected from a background of nanohertz waves, almost surely the murmur of supermassive black hole binaries assembling with their host galaxies. In the 2030s, LISA will tune to millihertz, tracing mergers and inspirals in space, and carrying the strong field grammar of general relativity to regimes that ground-based interferometers cannot reach. Together, these instruments turn dynamics into data, so that the growth of black holes becomes part of cosmology's general account. Where the cosmic ledger touches the particle ledger, the neutrino continues to confess in bounds. KATRIN's latest run halves the laboratory limit on the effective electron-neutrino mass, tightening the weave between cosmology's inference from structure and a tabletop's patience with beta decay. The next verdict may come not from mass but from identity. If neutrinoless double beta decay is seen, Legend and Cam Lanzan pressing their half-life limits upward, lepton number will be broken and leptogenesis, long a beautiful outline, will gain a laboratory credential. These are not marginal footnotes to existence. They are mechanisms by which a tiny asymmetry became a universe with chemistry. Protons, too, are asked to fail. Superkamiokind's long vigil has set lifetimes beyond 1034 years in classic channels, quietly pruning whole families of grand unifications. Its successor, Hyperkamiokin, nears completion of its cavern and installation milestones, aiming for operations later this decade with a volume that transforms rarity into reach. Each null result is a design decision by nature. The apparatus merely reads it aloud. High-energy physics evolves on a slower metronome, but its questions remain adjacent to cosmology's. Run 3 extends through 2026. Then the LHC sleeps for a long winter while it becomes the high-luminosity LHC. When beams return around 2030, the collider's yield will be multiplied, turning the Higgs sector into a precision laboratory. If subtle symmetries stabilize scales, if portals open toward hidden sectors, if rare decays betray new couplings, the discovery will not stay confined to Geneva. It will radiate outward, reinterpreting early universe dynamics, dark matter's identity, and the chemistry of why anything persists. Even constants are enlisted as hypotheses. Spectrographs pry at fine structure lines in distant quasars, while optical clocks, nested in quiet rooms on Earth, compare their ticks for signs of drift. The prevailing result is constancy within exquisite limits, yet the door is left ajar for small variations at early times that could shift recombination or drift the sound horizon. If ever a credible deviation appears, it will turn selection and dynamics from competing metaphors into parameters to be fit. Across these efforts, a method repeats. Redundancy is designed, not incidental. The expansion history is read 3 ways: supernovae, bow, lensing, and checked against the CMB's calibration of the sound horizon. Growth is measured by weak lensing shear, by cluster counts in X-ray and millimeter light, by redshift space distortions. Inflation is tested in the scalar tilt, in the Gaussianity of primordial fluctuations, and in the long chase for B modes. The baryon asymmetry is bracketed by cosmology and by accelerators, by the statistics of the microwave sky, and by underground crystals listening for forbidden decays. Each strand can fail independently. Only consistency survives. The portrait that emerges from this apparatus is not static. It is a living fit that tightens year by year, forcing models to become mechanisms and arguments to become numbers. Some initiatives falter and are rescoped, others eclipse expectations. What remains constant is the practice. Build instruments whose limitations are orthogonal, let the sky overrule preference, and convert surprise into design. In that way, the question that began the enterprise, why does a universe exist, and why in this key, moves from the horizon of philosophy toward the workbench of physics, not to be solved at once, but to be cornered by accumulation. For if existence is an equation with missing terms, the solution method is already known. Constrain the space of answers until the remainder is small enough to touch. The rest is patience, the quiet stubbornness of cryostats in the dark, of mirrors that do not blink, of clocks that agree with themselves. And somewhere, beneath the hum of detectors and the wind over domes, a thought persists, that in turning instruments toward the first light and the last fate, humanity is not merely measuring a universe. It is learning the grammar that allowed a beginning at all. Night gathers above the instruments like a slow tide. Domes close. Cryostats hum at their appointed temperatures. Distant mountains cool. The universe, indifferent to the schedules written on human calendars, proceeds under laws that never sign their own names. What the measurements have assembled looks complete from certain angles. Space expanding, radiation cooling, elements forged in brief fires and long furnaces, structure condensing from a faint statistical roughness, a late acceleration steered by a pressure no one has touched. Yet the question that started the inquiry does not ebb with the data. It sharpens. Why does any of it exist? Laws, numbers, fields, geometry, and why in a form that lingers long enough to wonder about itself? Philosophy enters here not as a retreat from knowledge, but as its horizon. A cosmos with a history implies a boundary condition. An arrow of time implies an origin of order. The equations that carry galaxies on their curves, Einstein's field equations, quantum field theory stitched to gauge symmetries, succeed magnificently at how. They legislate motion and predict pattern. They grant probabilities to outcomes and map which futures are permitted. But legislation does not tell why law holds any jurisdiction. The principle of sufficient reason, ancient and stubborn, asks that existence offer an account of itself. Physics answers with mechanisms and symmetries. The remaining silence is not failure, it is the shape of the frontier. One response hears necessity. Perhaps reality could not have been otherwise. Perhaps mathematics is not a language about the world but the world's substance, as if structures and relations are the ontology and matter only their costume. In such a view, the universe exists because certain equations must. Existence is the flowering of consistency. If the logic of numbers is inexorable, a cosmos that realizes them is not a surprise. It is an inevitability. This answer carries a severe elegance. It also shifts the weight a step backward. Why does consistency exist, and why does consistency feel like anything? Another response accepts contingency. The universe could have been different or absent. Its constants are not deduced but sampled. In the broad frame suggested by inflation and high-energy landscapes, regions may realize different low-energy laws. Only some produce chemistry, only some harbor long-lived stars, only some end up with a microwave sky gentle enough to permit galaxies. Observers, appearing late and local, inevitably measure parameters compatible with their own possibility. This logic, anthropic, statistical, respects data and selection simultaneously. It also struggles with infinities, with measures that quarrel, with the difficulty of predicting anything more specific than existence occurs where it can. For many, the view is not wrong so much as incomplete. A third response listens for dynamics deeper than current fields and metrics. If spacetime is emergent, if geometry is the macroscopic weaving of quantum entanglement, then initial conditions may be statements about information rather than about particles. The low entropy of the early universe, the special vanishing of gravitational degrees of freedom, could be the signature of a boundary state with minimal entanglement across emergent partitions. The arrow of time becomes a river not because time had to flow, but because the headwaters were arranged to fall. This is a perspective more programmed than theorem. Still, it reframes why questions in a grammar physics can parse. Given a microscopic description, what macroscopic states are typical, which are selected, and by what principles? Others turn to origins without edges. A universe may be described by a wave function whose most probable histories are rounded at the beginning, no singularities, no earlier time to speak of, only a quantum transition into classical expansion. Or it may tunnel from a state without classical spacetime at all, nothing, in the narrow, technical sense where familiar coordinates have not yet been drawn. In these pictures, the question, what happened before, loses its traction. The calculus yields amplitudes instead of narratives. The temptation is to call such amplitudes explanation. The caution is that amplitude is not motive, and even a calculable origin requires a meta-principle that selects the rulebook itself. Behind these frames, the constants remain. Vacuum energy whispers almost nothing and moves the late universe. Primordial fluctuations carry an amplitude fine enough to grow galaxies without drowning them. The matter, antimatter surplus is so slight it reads like a rounding error, yet it lifts the periodic table out of annihilation. Whether fixed by symmetry, scanned by dynamics, or sifted by selection, these numbers acquire an air of parable. Change them by a breath and the long sentence of stars and minds becomes shorter or never begins. The sensation this produces, fine-tuning, coincidence, design, luck, depends as much on temperament as on theory. The facts are firm, the interpretation provisional. Humanity's presence in this account is not an afterthought but a datum. Observers are late products of stars and chemistry, yet their arrival transforms which questions can be asked. Knowledge is not external to the universe. It is an activity happening inside it, in finite brains under finite skis. John Wheeler's phrase, participatory, is sometimes taken farther than caution recommends, but the modest claim is undeniable. Observation changes what is known. The cosmic story includes instruments pointed outward and equations turned inward, feedback loops where theory drives design and design returns data that revise theory. Meaning, in this sense, is not imported. It emerges as a relation between minds and world, a resonance rather than an imposition. The future the data imply complicates the poetry. If dark energy behaves like a cosmological constant, the expansion will continue to accelerate. Galaxies beyond a shrinking horizon will fade, and the local group will become an island amid thinning light. On timescales that embarrass metaphor, stars will exhaust their fuel, black holes will evaporate, and the cosmos will trend toward a thin, cold simplicity. The narrative arc, written in the thermodynamics of large systems and the quantum leakage of horizons, bends toward quiet. In such a vista, purpose is not found in destiny but in the present texture of law and chance. How a universe that hastens toward emptiness paused long enough to build complexity and thought. Meaning thus returns to the opening uncertainty, not a script assigned from outside but a coherence discovered within. All is not evidence. It is an orientation that keeps error from rushing in to fill silence with convenient tailies. Humility, in this register, is methodological. It holds confidence where predictions have been weighed against sky and accelerator, and it refuses to paste metaphysics over what the data have not invited. The balance is difficult, especially where existential hunger presses against finite knowledge. A mature cosmology learns to say both. This part is measured, this part is model, this part is hope. The question of nothing versus something acquires precision only when nothing is defined. Philosophical nothing, the absence of law, mathematics, possibility, cannot be a subject for physics because it permits no counterfactuals and hosts no experiments. Physical nothing, the vacuum of quantum fields stripped of excitations and geometry, turns out not to be empty at all. It fluctuates, lends its jitter to atomic spectra, and at cosmic scales impersonates a gentle pressure. If existence is said to come from nothing, the word smuggles in a great deal. Equations, symmetries, a Hilbert space that holds states before any state is realized. The honest statement is narrower and stranger. Within a lawful framework, states can emerge with calculable weights. The framework itself, so far, is taken as given. Some will call the ultimate givens brute facts. Others will expect them to yield under a deeper synthesis. History counsels patience. Geocentrism yielded to dynamics. Apparent coincidences resolved into symmetry. Anomalies turned into windows. Not every question survived. Some were replaced by better questions that made the old ones irrelevant. Whether "why does the universe exist?" is of the first kind or the second is itself part of the mystery. It may dissolve into a web of sufficient answers, mechanisms for smoothness and seeds, a microphysical account of asymmetry, a principle fixing vacuum energy, a unification where constants are outputs and not inputs. Or it may end at a lawful rock, beyond which explanation is not refusal but completion. This is the frame in which all further reasons are drawn. Meanwhile, the practice continues. Telescopes sharpen, clocks agree to more decimals, detectors listen deeper into quiet. The method is slow by design. It does not leap from wonder to conclusion. It moves by triangulation, by redundancy, by the virtue of instruments that can be wrong in different ways. In that slowness lies a kind of ethics, a refusal to let desire for answers distort the questions. The cosmos has been generous with partial disclosures. It has given a history where an eternity was once assumed, a map where myth once drew dragons at the edge, a set of numbers that seem absurdly accommodating to complexity. It has withheld just enough to keep inquiry honest. The closing image is simple, and it is true. The first light still washes the sky in microwaves. It carries the imprint of waves that rang when the universe could first breathe photons. The last light is far away in time and will not be seen by eyes, human or otherwise, unless the future finds ways to stretch longevity beyond imagination. Between those lights, there is a window where questions can be asked and answers can be checked. In that window, existence acquires depth not by decree but by description. If an answer comes, it may sound less like a revelation than like a conservation law, less like a proclamation than like a symmetry, less like a purpose than like a proof. Or it may be the acknowledgement that reason has reached the frame beyond which reason cannot speak without ceasing to be itself. Either way, the question has already performed a service. It has gathered equations and telescopes and generations of minds into a single gaze. It has turned attention outward and inward at once. It has measured not only the sky, but the patience required to read it. The credits roll over stars that have been dead for billions of years, their light only now resigning itself to night. The domes open for another run. The cryostats settle into their patient cold. The universe continues without commentary, and instruments without entitlement ask their next precise question. The mystery remains, not diminished by knowledge but clarified by it, not solved by a single sentence but made articulate by 1,000 careful ones. The answer, if it exists, is somewhere inside the coherence that already holds, a law that is also a landscape, a beginning that is also a transition, a nothing that is already structured enough to give rise to something. Until then, the cosmos speaks in the only voice it has ever used, a hum of ancient light, a geometry that remembers its source, and a silence big enough to hold the reason for being.